Welcome back, everyone. Today we're going to continue our work with 5.1, verifying trig identities. I'm actually going to start at the beginning and teach this lesson from the very beginning. Even though we've done some stuff in class, we're going to pretend like that didn't happen. This is going to be a bit of a monster video because it covers actually 3 days of instruction, one of which we've already done. We're going to start our flex learning on day 2. So this is your workload for the 3 days of instruction that go along with 5.1. Again, we're starting on day 2 on the first day of flex learning. And the first thing I want you to do is read the flex learning guide that I've posted on my website. If you haven't already noticed, your whole schedule is posted up on my website, Cadera Math. That's what we're going off of. The assignments are posted as usual. Answer keys are posted as usual. The only difference is that you'll be giving me some formative responses through the form of a Google form. All right. Without any further ado, let's go into the heart of the lesson and let's start at the very simple. Back in the day when we were dealing with the unit circle, we developed these 4 definitions based off of X and Y coordinates. And you just need to have them memorized because they're going to come into play shortly. And I think most of you do have them memorized, which is great. Understand that there is just a little bit of a corollary that is an immediate result from one of these. So if you have tangent squared, basically the long and short of it is that instead of being just a plain sine over cosine, that it would be sine squared over cosine squared. And you can do that with any of the cosecant, secant, cotangent, tangent functions. If it's squared, everything's squared. If it's plane, everything's plane, and so on. The next thing we developed was the Pythagorean identity, which again we worked off of the unit circle. We started with some random triangle drawn in with a random angle, and we were able to label the x and y coordinates and thus apply the Pythagorean theorem because it is, after all, a right triangle. So substituting in, we got our first Pythagorean identity, which is sine squared plus cosine squared equals 1. And then we worked those further by taking what we already knew and then doing something clever, because it's an equation. We're allowed to divide by whatever we wish. So the first one, divide by sine squared, and that results in right here it becomes a 1, right here becomes a cotangent, and right here it becomes a cosecant. So we end up with this version 2 of the Pythagorean identity that is basically the same thing, but just has some things that it doesn't just have sines and cosines now. We're able to adapt it to fit our needs. We can do the same thing, but dividing with a cosine squared and end up with yet a third version that involves tangent and secant. Altogether, these are the 3 versions of the Pythagorean identity, and you either need to memorize them or memorize the first one and know how to get the second 2. Now in this section, this is what the problems are going to look like. You're going to be presented with this statement that says verify the identity, and then it's going to give you an equation. What I need to point out is that they're saying verify that this is true. So initially, your job is to prove that this is true, so you can't assume that this is true. So we're actually going to completely ignore the fact that they gave us an equal sign, and we're going to work with one side and make it look like the other. Or in fact, there are actually 3 ways to do this. We can start with the left side and make it look like the right side. We can start with the right side and make it look like the left side. Or we can start with both sides and meet in the middle somewhere so that they are proven equivalent. Now the actual techniques that you're going to use each time are basically the more problems you do, the more experience you'll have and the better decisions you'll start to make. You're going to get jammed on a few problems, but this is where I would say start. This is organized in terms of kind of a hierarchy. The top ones you'll use more than the bottom ones, but that doesn't mean that you're going to use the top 2 every single time. So firstly, start with the more complicated side. Think of it like a simplifying problem. If you can get something simple, it's easier to get the other side simple as well. The next tier of most common things in the pink here is that you'll probably see an opportunity to use a Pythagorean identity or write all the non-sine and cosine functions in terms of strictly sine and cosine. The next tier is dealing with fractions and foiling and factoring. So you can find a common denominator to do an actual addition or subtraction problem between 2 fractions. You can split a numerator of a fraction into 2 separate fractions. I'm going to show you a couple problems where you FOIL. I'm going to show you a problem where you're actually going to introduce something, the conjugate, in order to get something that you want. Overriding advice is to say don't be afraid to start, stop, fail, and just try a new topic. Step away from the problem, come back with fresh eyes, and try it again. All right, so let's get into it. This is our first example, And you can see right away that they give you this direction that says verify, and they give us this equal sign that we're not allowed to assume. So the first thing I want to do is actually cover that up and pretend like it doesn't exist. Basically, this is now a game where I have to make the left side look like the right side or vice versa. From there, I'm going to look at that strategies list and just see what I can do, and I'm going to kind of look at the stuff at the top more often than I'm going to look at the stuff at the bottom. So in this particular problem, I see a lot of trig functions squared, and in particular, I see this one right here. That's the Pythagorean identity version 1, which means that I can just replace that with a 1. So all of that was equivalent to a 1, so I've just straight up replaced that. And then all of a sudden I've got this Pythagorean identity, which I believe is version 2 as we had it sit, and that identity says that we can just replace it with a cosecant squared, and then all of a sudden the left side matches the right side, and that is verified. The second example I have for you is right here. Again, I'm going to cover up that equal sign just to start off. A pretty simple problem, but there is more complexity on the left-hand side, so I'm going to start on that side. And there's nothing squared. There's no 1, so I'm thinking probably not a Pythagorean identity. So let's go to the next most common thing, and that is just to rewrite things in terms of sine and cosine. If you do that, you'll notice that a pair of sines cross out, and then you're left with 1 over cosine, which is the same thing as secant. So in this instance, I actually did something to the right side as well. I converted a secant to 1 over cosine to make both sides match somewhere in the middle. Our third example is right here. You'll notice that, again, no stuff squared, no 1s. There's a couple ways to do this problem. You can actually do this problem by converting to sines and cosines, but the main mechanic of it here is that we've got one fraction subtracting another. So I think that the authors of this problem intended for us to actually do that subtraction. In that respect, if I wanted to do that subtraction, I do not have the same denominator. So I need to make a common denominator, which means this one, we should go to a common denominator of sine times cosine, which means this one's missing a sine and this one's missing a cosine. So let's just, again, cover up the equal sign, we'll isolate our fractions, and then let's introduce what they each need in order to make that common denominator. So I'm going to multiply by a fancy version of 1. Remember, it's got to be the same thing top and bottom in order to retain the value of the original expression. Multiply straight across when you're doing fraction multiplication. So this is going to become a sine squared. This is going to be a bit of a mess, and this is going to get our desired common denominator of cosine times sine. So let's work on that numerator, this cosine times secant thing. For this, I'm going to actually convert that to 1 over cosine. So I'm going to write this down, and I put a 1 under the cosine that I originally had right there, just so that it assists me in doing that fraction multiplication. And then I can see that I've got these cosines that cancel out. So I can just replace that whole thing with a 1 right here. And then, so this whole thing is 1, and I can actually do this subtraction. So I've got 1 minus sine squared up top. And when I'm doing fraction addition or subtraction, I just keep the denominator the same. Then I know to say I've got a 1 and a trig function squared. That might be a Pythagorean identity, so I'm going to do some side work. I'm going to pull out the first version because it has a sine squared in it, and I'm going to see if I can get this thing in the red out of this thing. And you may notice that if you treat this like an equation and you subtract a sine squared from both sides, that this side on the right will now match exactly what I have in the numerator. So I can replace this numerator with cosine squared. Plug that in, and I've got this expression now. Now I've got one term over a denominator, and I've got cosine over cosine. So one of the cosines is going to cancel, and one of them, a cosine is going to cancel from top and bottom, leaving you with 1 on top and 1 on the bottom. And then I've got cosine over sine, and well, let's just convert cotangent to cosine over sine to make it match. Okay, the next problem, I haven't even bothered to write down the equal sign. I've just blocked it out, and I've got this expression on the left and this expression on the right. The one on the right, maybe I could convert to sine and cosine and do the actual fraction addition. But I wanted to do one where I can just split the numerator right here. So I have two terms separated by addition on the numerator here. So I'm actually allowed to split those fractions up just like that. So I'm basically undoing an addition problem, just like the previous problem that we actually did the subtraction. Well, I'm undoing that addition or subtraction there to split that up. That being said, then now look, I've got 1 over cosine and I've got sine over cosine, which is exactly what I have on the right hand side. So that just does a straight up verification right there. The next problem looks very, very similar, but it is very different. On the left-hand side, you can see here I've got this 1 plus cosine. Now you might be tempted to split it up across the denominator, but you can't do that because remember this is like there's an implied set of parentheses around here, and you can only split a denominator over a product, not addition or subtraction. I could split the numerator here. I'm not going to do that this time. I'm just going to see where this goes. One of the techniques at the very bottom was multiply by a conjugate, and right here I see 1 and I see cosine, but the cosine isn't squared. So my indicator from experience is that, okay, I've got this thing 1 plus cosine, it's not squared, and I don't have any way to rip it apart or turn it into anything else that I have. So I'm actually going to make things more complicated. I'm going to start on this side, I'm going to make things more complicated. I also notice that I have a matching almost matching pair right here, and these two are conjugates of each other, so that's another clue that I might want to multiply by a conjugate here. So what I'm going to do is I'm going to multiply by the conjugate of this denominator on the left side. I could have chosen this side to multiply the conjugate. Both probably work. I'm just going to go off of this side to start off with. Remember that a conjugate is exactly the same thing with a negative or the opposite sign. So if this were a negative, then I would do 1 plus cosine right here. And then we're actually going to do this multiplication. So this one, I'm not even going to bother to distribute. You could. I'm not going to advise that you do that unless it becomes necessary later on in the problem. But I am going to have to do this down at the bottom here. As you do a few of these problems, multiplying by the conjugate, you'll notice that there's a simplistic result that you can get. But I'm just going to straight up FOIL here. So I'm going to go first terms, outer terms, inner terms, and last terms together. If I do that, I get 1, a positive cosine, a negative cosine, and a positive cosine squared. The nice thing that happens when you multiply a conjugate, this is why we care, is that these middle terms always cancel. And it actually makes the bottom fairly simple. And you might recognize that is, well, now I have something squared and a 1. So I'm going to try to tease out a Pythagorean identity if I can. And if I start with the version 1 over here and subtract a cosine squared, that's exactly what I get. So I can substitute in a sine squared on the bottom there. And then I'm lucky enough to have something cancel. So we have 2 sines on the bottom and 1 sine on top. And now if I had distributed that sign earlier, I'd have a bit of an issue there. I just have to factor it out again, but that's no big deal. Cancel them out. And then you have the same thing on the left side as you have on the right side. The next example I have, the second to last one, is a simple one. I just wanted to show you one where factoring actually comes into play. You'll notice over on this side, the more complex side again, I have a cosecant involved with both terms. So what I'm actually going to do is I'm going to pretend like I'm factoring out undistributing a cosecant. So that replaces that first term with a 1, and what's left over is a 1 minus cosine squared. Then that is a Pythagorean identity like we just did with the previous problem, so I don't have to repeat that work. I've got it sitting right there, so let's replace that with a sine squared. At this point, I think let's convert to all sines and cosines rather than that cosecant. So it looks like that. One of the signs cancels, and I'm left to a sine of x. Okay, the next example is probably the most complex one. And that's because I'm choosing to do one through FOIL, even though I could actually do a Pythagorean identity replacement right there. That's version 2 or 3, I forget which one. But the issue is that this one's not replaceable because no matter what you do with a Pythagorean identity, the version 1, either the sine squared term or the 1 would have to be negative in order to do a direct replacement. So I could do a replacement here and then distribute, but I wanted to demonstrate foiling too. So I'm just going to straight up FOIL throughout here. That gets cotangent times sine squared, or cotangent squared times sine squared. Then we have cotangent times 1 and 1 times sine squared. And then we have 1 times 1. So we have all 4 of those terms there. Now what can we do with that? Well, let's start hunting around. I see some stuff squared. Do we have some 1s in there? Yes, we do. And you look a little deeper and, well, let's not go there first yet. Let's go to fixing this right here. So I'm going to change this into a cosine squared and a sine squared. The sine squareds cancel. Those are gone. So I have a cosine now. And now let's pay attention to this cotangent squared plus 1, which is version 2 of a Pythagorean identity. And basically replace that with a cosecant. So we're using this right here to replace those 2 terms with a cosecant. And then all of a sudden we've also got this cosine squared plus sine squared that is exactly version 1. So I can replace that bit with a 1. And then I look at this and I look at this and they don't look very similar. And I'm kind of freaking out. There's something weird right here. It's a 2. And I don't see any 2's over here. I don't see any 2's over on the left-hand side. So I do a little something clever here, and I turn the 2 into a 1 plus 1, and then all of a sudden I've got a Pythagorean identity again. So I do a replacement there with a cosecant squared, and all of a sudden I've got the same thing on left side and right side. The last thing that I want to do with you here is just kind of take a look at the problems that I've done during this video. And I understand that this is something new and weird, and you may not have the experience to see, but can you look at the problem and determine which method you want to use? Take a look at the problems that we've done, take a look at the strategies that we've used in the middle, and see what's in common. Well, here we've got stuff squared, identities, okay? Here we've got a pretty simple expression, both of which are not in terms of sine and cosine, so maybe we want to rewrite. Here we've got a straight up subtraction problem that's just basically shoved in our face, so that's probably the one right there. This one's got something in common to both terms, so this is our factoring problem. Here's one where we've got a binomial times a binomial. Now I could do a replacement there, or try to do one there, or even try to do one here. But we could FOIL this out. We've got lots of options on this problem. This problem, I chose to do a conjugate because, one, I can't split up that denominator, but also I see that I have a conjugate pair sitting right here. So that's an indicator to me that I'm going to use a conjugate pair. And then this could also be a conjugate pair problem. It wouldn't surprise me at all. But the other thing I can do, I can split up this numerator, and since I have addition here and I don't have two things being added here, I'm thinking split on this one. So just understand that your first task when you're doing these alone is to figure out what you want to do, and that may not always be obvious, but by looking at all of these problems and all of these strategies on one page, maybe you can identify some visual clues as to why you do one method over the other. Again, to reiterate, here's your work for each day. I'll see you next time.